This is just a brief introduction to the possibilities of multiple states in simple atmosphere and ocean models. So this is first one is multiple equilibria in a simple atmospheric model, where we go back to our energy balance equation we used in terms of the change in surface temperature given the solar radiation, albedo, and the outgoing long-wave radiation, where we assumed from Sellers and Budico type work albedo that's temperature dependent in the range. They were looking at ice age transitions and came up with this. Well, basically Pierre Sellers came up with this, and we also looked at ice albedo feedbacks, where we looked at albedo and surface temperatures with the positive feedback in either direction, melting of the glaciers or building of the glaciers. So two plausible parameterizations for an energy balance model were looked at. The signs next to the arrows denote the correlations between the changes here. We already talked about it. Warmer surface temperature, reduced snow cover, reduced albedo, and increased so increased radiative balance basically means trapping more heat and leading to warmer temperatures. But this net is positive because of two negative signs. So we can also see a similar behavior. There have been so-called snowball Earth episodes in Earth's history, where glaciation came down to very low latitudes, which is not easy to do, just in terms of losing enough energy to glaciate into the tropics. And also there are some debates about how biology would have survived, how life in the ocean even would have survived if the entire planet was covered with ice. So then it is turned into a slush ball world rather than a snowball, slush ball Earth rather than a snowball Earth, and snow, and so on and so forth. Without going into the details of the snowball Earth episodes, what we do know is that the solar luminosity was 30% lower when the solar system got formed, and the solar physics is such that nuclear fusion constantly increases the luminosity and the energy coming to Earth. So Sun is also expanding. So in about 100 million years, temperatures on Earth would be about 100 degrees centigrade, which means all the water vapor would evaporate. In 5 billion years, Earth would Sun would disappear by burning all the fuel, and so on. So if we look at the energy flux from the Sun, take two scenarios where the way solar flux has evolved and a 0.85, so 15% less solar flux at the top of the atmosphere, then you can see that the temperature dependence of the albedo produces several equilibrium solutions. Stable states are these filled circles, and an unstable equilibrium state is also possible, which means the Earth's climate can go into that state, but it won't last very long. It'll flip back to this state here. So if you're here, it'll flick back to here. If you're here, it'll move to here. So you have, but these can last for a long time, so they are stable equilibria, whereas these are unstable equilibria. And we can produce that by basically taking this equation, using the albedo relation, and writing it in this form, where the dependence of temperature on solar flux is written in terms of energy balance for outgoing long wave radiation. So you can choose a range of albedos based on your assumption about the extent of snow cover and extent of snow cover and ice cover. So basically, in a very simple, you can consider this as a simple atmospheric model, which is what we did in chapter 2 and 8, where we looked at energy balance as averaged one-dimensional balance of incoming energy and outgoing long-wave radiation, incoming solar energy, outgoing long-wave radiation. And you can we also did it as a zonal mean, meridional mean box of height h, and so on, when we wrote the energy balance equation in chapter 2, right? So it had a heat capacity and it had a height h. We can think of scale height, and then it had alpha, which could be temperature dependent. Okay, so can similar relations also be produced in a simple ocean model? Of course, yes, but then the question is, we know that unstable solutions have occurred in the past in terms of snowball Earth, which was short-lived, and then the system jumped out of it. So it went into the snowball Earth and then jumped out of it. Similarly, you can think of what other multiple equilibria can occur in a simple ocean model. Question, of course, is that these simple models, the one we looked at before for the multiple states, and these are done in simple models, which are more like fitting observations and finding realistic parameters to tune the model and say, yes, these are possible, but you don't explain the full system with them in terms of the processes. For example, when we related the northern hemisphere temperature flips to southern hemisphere temperature change, we didn't say exactly what can cause the flips in the northern hemisphere, other than to say that shutdown of the shutdown of the North Atlantic deepwater formation can do that. But what would cause the shutdown of the North Atlantic deep water? We talked about a freshwater lens being formed by a sudden release of fresh water, let's say from Greenland glacier melt and so on. But so you need to use real models to see if such multiple states are possible. So observational evidence exists, simple models can produce them, and we have to confirm them with real models. Okay, so a two-box model is used to go back to the idea we discussed way back in chapter 8, where we said the relaxation timescales or the decay timescales for temperature perturbations and salinity perturbations are very different, and these can lead to multiple equilibria in the system, right? So depending on the depth of the column of water you are looking at in a box, you can formulate a problem where you can look at the relaxation time of salinity and temperature perturbations. So a two-box model of the thermohaline circulation can allow us to do that. Jakub Moravska did that in 2000, related to the basic idea proposed by Stommel way back in 1961. So here a low latitude and high latitude box is assumed with a temperature T1 S1 in the low latitudes, T2 S2 in the high latitudes. Colors indicate cold temperatures, warm temperatures. The temperature difference delta T, T1 minus T2, can be assumed to be constant, and you can have water fluxes, so you can take precipitation from here and dump it onto here, for example, which results in a surface flow of temperature and salinity, where you have water flowing in this direction, and you can have a compensating bottom flow coming from high latitudes to low latitudes. You can think of this as a direct circulation, where water is sinking in cold latitudes, just like Hadley cell, where air rises in the warm part, whereas Ferrel cell the air is sinking in the warm part and rising in the cold part. So we talked about thermally direct and indirect cells there. So you can do simple formulations. The water transport can be defined as some coefficient times the density difference between the cold and warm boxes, which can be written in terms of temperature and salinity dependence of densities, which we did before in chapter 8, where we had a second order term here, but we have dropped that here with gamma equal to 0. So you can write then the salinity equations for the two boxes. ds1 dt is related to the water flux times S2 minus S1 plus P, where P is greater than 0 denotes net water flux. So we have net water flux out of here, net water flux into the ocean here, which means salinity is increased here and salinity is decreased here, for example. You can use the magnitude of Q because the direction of transport doesn't matter for these equations, and ds2 dt can be similarly written as magnitude of Q times S1 minus S2 as opposed to S2 minus S1 minus P. So those are just salinity conservation equations for exchanging of water between the two boxes. So stationary solution for this is only possible if delta S equal to S2 minus S1 is this expression when Q is greater than 0. So when water is flowing from the warm box to the cold box, so you can evaporate here and precipitate here, for example. So you have thermally direct circulation, or the other way where you can take water from there to there. So you can have a stable solution for minus alpha delta T. So this expression where Q is less than 0, which means you have an indirect circulation happening, water sinking in the cold, water rising in the cold part and sinking in the warm part. Okay, so here delta T is assumed to be T2 minus T1 less than 0. So the warm box is always warm. We don't allow the temperature gradient to reverse. Okay, for direct circulation, Q is greater than 0, so water is being taken from the warm box and moved to the cold box. So rho 2 is greater than rho 1, so warm box is lighter. Here two solutions are possible, one with a smaller contrast in salinity, delta S is less than 0, and one with a large negative delta S. For an even smaller delta S, an indirect circulation exists. So Q is less than 0, so water is actually rising in the cold box, moving to the warm box. So rho 2 is actually less than rho 1. So we put delta equal to minus beta delta S or alpha delta T, write E as a parameter of beta P or rho 0 K alpha delta T squared, and we obtain from this equation again delta is 1/2 plus minus square root of 1 over 4 minus E for transport, let's say northward, or 1/2 plus square root 1 over 4 plus E for transport being southward, remembering what Q is, right? So stationary solutions again for can be, why did I repeat this? Okay, just to show the equation again. So did I go wrong? Yes, I went in the wrong direction. So the transport Q is given by K rho 0 alpha delta T times 1 minus delta. So it depends on the temperature gradient between the boxes plus the salinity, relative change in salinity and temperature, remembering that we have very different relaxation time scales for delta S and delta T as we talked about before. So here multiple equilibria in the unstable regime here and the stable regimes here are possible for the thermohaline circulation for different values of the water flux in the Stommel box model that we had looked at. So this is the water flux E, and this is the north-south salt contrast delta. and you can see that there is a direct circulation here where water is being taken out of the warm box, moved to the cold box, and here it's a you can in this range of salinity contrast, you can have an unstable solution where the flux reverses back very rapidly and the solution goes to the indirect circulation. So you can have a stable indirect and direct circulation with this rapid transition happening in some range of delta. Okay, simple ocean model, but you can produce multiple equilibria. Or you can also think of it this way, that for this value of flux, for example, you can have a stable solution here and a stable solution here, depending on the north-south salt contrast, or for each salt contrast you need a certain flux to get a direct solution or an indirect circulation. Okay, so think of it either way. So this is like a bifurcation point where you can go in this direction or in this direction. Okay, so this is stable for these range, whereas this is unstable because it doesn't last here. It'll just go there or come back to here, depending on the salt contrast and the processes of water transport. Okay, so remember that that's the water flux E that's normally used to show potential for multiple equilibria. Finally, the schematic depiction of the thermohaline circulation and the meridional heat and water fluxes. So in the direct circulation, you have water sinking where it is cold, so you have a stable looking profile with warm temperatures near the surface, cold temperatures in the deep. So this is what we have in the modern climate. We have transport of heat and mass towards the cold latitudes where deep water forms, and there is an atmospheric heat flux that corresponds to that. Here you have atmospheric freshwater flux, so this is an indirect circulation which is stable. So you have atmospheric freshwater flux dominating this way, and you have water sinking and creating this salinity profile, which is very high salinity at the surface and lower salinities at depth, which is a reverse of what we have in the modern times, where surface salinities are lower than the subsurface salinity. So you end up with two types of indirect circulation with water sinking in warm areas. Okay, so arrows of the water circulation are color coded. Red is warm and blue is cold and fresh, and green is salty. So you are moving salty water, sinking cold fresh water, and creating a reverse circulation. Whereas here you are moving warm water southward, so you are again moving atmospheric heat flux in that direction, but this is much higher than in the direct circulation. Okay, so here you are sinking water in the warm side and supplying the rising of the water in the cold side. Okay, so in the past there are some arguments that this has happened, and there are various parameter ranges in which this can be interpreted. So here you can see that the stability of temperature is very low compared to the direct circulation, and you have also a atmospheric flux going in this direction, and heavy salt cold fresh water moving here, and salty water sinking in the low latitudes and going north and coming back. So obviously various range of solutions are possible by tinkering with delta S and delta T, and corresponding atmospheric fluxes have to occur. in heat and fresh water to sustain these solutions, to stay in the stable regime. Okay, so it's just a quick example of how a simple atmospheric and oceanic models can produce multiple equilibria. We will leave this here and look in the next podcast whether in coupled climate models such multiple equilibria occur, so that we can confirm that these are realistic solutions and what is inferred from paleoclimate data are possible in the real climate system, and they are not just artifacts of paleoproxies or interpretations. Okay.